Okay. Hello, everybody. My name is Matthias. This is Martin. We're going to talk about bufferization in MLIR, which is the process of going from tensor IR to MemRef IR. So this is a tutorial, so we're going to show you a bit of the more practical aspects, how to use the bufferization framework, and also some code later. So we're going to use this as a running example. So we're going to see this a few times throughout this presentation in various forms. So what we have here is a tensor matrix multiplication, a batched one actually, which is completely expressed in tensor IR. And as you can see here, this is in a function which has buffers already given to this function. That's a pattern that we see very often in compilers, that the buffers are already pre-allocated by some runtime, by some compiler. And it's connected to this tensor matmul via these bufferization to tensor ops, which basically turn these buffers into tensors. You can think of those as a kind of unrealized conversion cast, and these will be resolved throughout the bufferization. At the very end, we have this bufferization materialize in destination, which says that this computed tensor %0 should actually be stored in this buffer %c. So this is a kind of output buffer here. One more word about this bufferization to tensor op here. You can see it has this restrict attribute. It's a unit attribute. And that one actually has to be set, otherwise your IR will be rejected by the MLIR bufferization framework. And what that says is that in this case, this bufferization to tensor op is the only bufferization to tensor op in the entire program that makes available %b or an alias thereof to the tensor IR. So this is very similar to the C or C++ restrict keyword. And this basically tells the bufferization that there is no other thing coming into the buffer, into the tensor IR that may be aliasing with %c. So in this example, that's clearly violated because we have a subview of %b and it's also passed to a bufferization to tensor with a restrict keyword. So this may miscompile. Maybe one more word about this. So these ops that you see here, bufferization, materialize in destination, and to tensor, some compilers have their own variants of these ops. For example, in the ERI compiler, there are these flow dispatch tensor load and flow dispatch tensor store ops, which basically do the exact same thing. They just don't operate on MemRefs, but they have their own buffer types at the boundary. So this is an overview of what we have currently in the bufferization dialect. And these are the steps that we have in bufferization. So we have a bunch of passes in preprocessing, then bufferization, buffer level optimizations, and then buffer deallocation. And today we're going to talk about the underlined ones. So we're not going to talk much about buffer level optimizations. But if you have questions about any of these, please approach us after the presentation. Good, let's start with bufferization. So bufferization, as I said, is the process of lowering tensor IR to MemRef IR. So tensors in MLIR are immutable. They don't have memory location attached to them. And so in order to execute it, you have to bufferize it. And that's when you assign actual memory locations, and that's when you can run the program. So we have a pass for that. It's called One-Shot Bufferize. It's also exposed to the transform dialect via this One-Shot Bufferize op. It's op interface driven. So that means if you want to bufferize your own ops, you just have to implement this bufferizable op interface. And then you're good to go. So here's an example of what bufferization does. We have a very simple function here that just inserts a float into a tensor that's given to us from this function basic block argument. And when you run one-shot bufferize, then you get this output here. And one thing to note is that the function signature has not changed here. So it's still tensors, but we have these bufferization to MemRef and to tensor ops at the boundary here. And that's the default behavior. By default, we don't touch any function signatures. And that's generally a bit safer because it can be a bit hard to predict how will the signature change. Also, you see that we have an allocation here. That's, again, because we didn't bufferize the function signature. The bufferization framework doesn't have any knowledge about the function basic block arguments. Am I allowed to write into the future buffer of %t, these kind of things. That's why a copy is created here. And we store into that copy and return that. So you can change that. We have a flag for that, bufferize function boundaries. And as you can see, now the signature was bufferized. We return a memref. We directly store into that buffer in place. No copies anymore. Also, you can see that we have these MemRef types with fully dynamic layout maps. If you don't like that, there's a flag for that. You can set it to function boundary type conversion equals identity layout. And now you have very simple MemRef types without a layout map or with the identity layout map. So here, in this example here, I put an annotation to this function basic block argument. So I said bufferization writable equals false, and that that tells the bufferization framework that I'm not allowed to write into the future buffer of %t. And now we have our copy back. There are other flags that you can, or other attributes that you can specify for basic block arguments. For example, you can also specify a layout map. You can specify the memory space, and that gives you quite a lot of control over how stuff is bufferizing. So let me talk about destination passing style. And that's really a kind of, that's really a type of op that the bufferization framework was designed for. So ops that are in destination passing style have one thing in common. They have a relationship between op results and op operands. So in this example, the tensor result of this tensor insert op is tied to the tensor op operand. And what that means is that after bufferization, you're guaranteed that the result %r will be in the same buffer as %t or in a brand new buffer. And this really makes bufferization much easier because the bufferization analysis doesn't have to think about, okay, where do I put this result? It's either %t or it's a brand new buffer, but not some other buffer that may be available. So in this case, %t was used directly. There's no copy here, and that's what we call an in-place bufferization. Ops that implement the ops that are in destination passing style implement the destination style op interface. And this op interface is not only used for bufferization, it's also used for other transformations such as tiling. Here's an example where the %t, this op operand, did not bufferize in place. So here the bufferization, for some reason, decided I cannot store the result into the same buffer as %t. And an example for that could be that the original value of %t is still needed. So if you write into it, we can't read data that we still need later. Or maybe %t is not writable. So that's what we call an out-of-place bufferization. And yeah, we allocate, copy, make a copy of the buffer, and use that buffer from that point on. So I want to highlight that this bufferization framework, as I presented it now, does not give you any guarantee until this point that a result will end up in a certain buffer. In particular, there's no guarantee that the result will be in the same buffer as %t. It could be a brand new buffer. If you want to make sure that something is in a buffer after the computation, then you have to use this op that I showed earlier, bufferization.materialize in destination. This really tells the bufferization framework, I need this result in this specific buffer that I specify here. We have a few more examples about that later. Here's an op that's not in destination passing style, tensor from elements. It's not in destination passing style because this result does not have a tied op operand. And those ops, they don't bufferize that efficiently. You can see there's an allocation here, which you may not want. But that's why this framework was, as I said, really designed for destination passing style ops. If your op is not in destination passing style, you get an allocation. How to address that issue, I will show later. Most ops that we deal with, in our work at least, they all happen to be in destination passing style, but also because we designed them that way. Here is an example how to implement the bufferizable op interface. This is an example for tensor.insert. And if your op is in destination passing style, the implementation is very easy. So you just need to implement one interface method, the bufferize method. In here, there's a certain API that you have to use, but also this API is pretty easy. You can take a look at it later. Basically, there's like a helper function, get buffer, and there's a function replace op with bufferized values. And these are the only two things that you have to use. So these op interfaces or this bufferizable op interface is typically implemented as an external model. That's how we did it with all the dialects so far. It's usually in the respective dialect in the transforms directory, and there we have this bufferizable op interface impl.cpp. So if you look at the MLIR source code, you find a similar file in many directories of many dialects. So here's an example for an op that's not in destination passing style. So this is a tensor.pad op. It's not in destination passing style because the result of a tensor.pad is a tensor of a different shape. And because of that, it cannot implement the destination style op interface. So this bufferizes to a near location. So because of that, you have to specify that in the bufferizable op interface. So basically, the first four methods here describe how this op is being lowered before we actually rewrite any IR, so that the bufferization framework can run an analysis. This bufferizes memory read function tells the analysis that after bufferizing this op, there will be a memory read side effect on the first tensor op operand. So this op only has one tensor operand. That's why we don't need to check what operand we're given here when this function is getting called. Also here, I want to highlight that this getAliasing values function describes the tying relationship between results and op operands. And because this returns a brand new allocation, there is no aliasing or tying relationship between the operand and the result after bufferization. That's why this simply returns empty set. And finally, you have to implement a getBufferType function. This function is used to predict the future buffer of a result or basic block argument before the IR is actually modified. So the reason why this is needed is mostly for loop bufferization, because we bufferize ops from outside to inside. That means before we bufferize the contents of a loop, we bufferize the loop itself. And for that, we have to know which, if there's a eta arg, a tensor eta arg, we have to know which MemRef type to assign for that. And that's where this helper function is used. So that's what you also have to implement. And of course, the bufferize method, which I don't show here. Here are a few common pitfalls that we're seeing with bufferization. One example is that sometimes people forget to register the external models for the bufferizable op interface. So for those who don't know, external models are a way to implement an interface in MLIR without specifying that at the op directly. So we typically don't implement it as part of the op directly. We put it in this transforms bufferizable op interface impl.cpp. But then at some point in your program, you have to register that with the dialect registry. So in MLIR, this is done in this init all dialects.h header file. In your own compiler, you should probably have your own header file that loads all dialects that you need and registers the external models. And ideally, only the ones that you need and not the entirety of MLIR. Another common pitfall is that you want to bufferize the function boundary, but you forget to set the flag. What we also see is that getBufferType is sometimes not implemented. People forget about it. And then at first, everything looks fine, and your op bufferize is perfectly fine. Then you put it inside of a loop, and now suddenly you get invalid IR. And typically, the kind of error that you see is that some values are yielded from the loop, but the type of these yielded values are different from the eta arg type that the loop has. So that's an indicator that this function is either incorrectly implemented or maybe that you didn't implement it at all. Another common one is that input IR with two tensor ops but without a restrict keyword, or that you have that you completely ignore the memory space, and if you just care about CPU compilation, that may be fine. But if you do GPU compilation, it's important to put the right memory space for shared memory and so on. So you have to take care of that in this getBufferType and bufferize functions. Also, as I mentioned before, you cannot make any assumptions that a computation may end up in a certain buffer. If you need that, you have to use this bufferization.materialize in destination op. And finally, we currently have some limitations with respect to loop bufferization. And loops that look kind of like the one that I have down here, they don't bufferize very efficiently. Additional copies will be inserted here. And the issue here is that we're yielding these eta args, these tensor eta args, in a different order. So we're first yielding the second one and then the first one. And that's just an implementation issue at the moment. We're going to address that at some point. But if your IR looks like that, you get additional copies. Same thing happens when you yield something here that was defined outside of the loop. But in all the workloads that we actually encountered, this is not usually the case. Usually the loops are very nicely structured, where you have some buffer or some tensor that you update throughout the loop, and you just pass it again as you yield it to the next iteration, modify it in the next iteration, and it's just getting passed through in a very regular fashion. Good. Let me talk briefly about conflict detection in One-Shot Bufferize. And this basically describes how One-Shot Bufferize decides whether a tensor copy or whether a buffer copy is needed or not. And we're basically looking for three things. We're looking for conflict triplets, which consists of a definition, a potentially conflicting write, and then a read in that particular order. So what does that mean? We have a tensor from elements here. This is the definition. This defines some computations, the result of some computation. Now here we have a conflicting write into, well, this is not a write, it's just an update, but a tensor op. But here we store something into %0, and down here we extract from %0. And because of that, this write here cannot be in place. So if we would directly write into the future buffer of %0 here, we couldn't do this extract down here anymore. And that's why the bufferization framework will insert a copy here for the insert. And by the way, the same thing happens. This also takes into account any kind of aliasing. So extract slice, for example, creates an alias of %0 here. So this bufferizes to memref.subview. So it doesn't matter if you use %0 here directly or if it's %0 alias. The bufferization takes care of all these cases. So again, what we're looking for is a definition. After that, a conflicting write, and then a read. If it happens in that order, then we have a conflict. If stuff happens in a different order, we have a definition, then we read from it, and then we write to it. That is perfectly fine. There's not a conflict. Another example of what's not a conflict is if we have a definition, we have a write to a part or a slice of that tensor, and then we read a different slice of that tensor. That's also not a conflict because these two slices here are not overlapping. So the support for this is still somewhat limited in One-Shot Bufferize. So if this overlapping relationship is obfuscated through some block arguments and is not directly visible that these things are not overlapping, then you might still get copies. So this is actually looking directly for extract slice, insert slice pairs. And finally, one thing that I want to mention, there are special rules for loops. So usually, as I said, definition, read, and then write is not a conflict. But if the definition is happening outside of a loop and the read and the write are inside of a loop, then this is still considered a conflict. Because the first iteration would write into the buffer, and then we go to the next iteration, it tries to read the original value, and we already overwrote it in the previous iteration. So this is also a conflict. Good. So at this point, I want to give you a short demo of how to use the bufferization framework. And we're going to take a look at the small example here. So this also highlights a little bit the integration into the transform dialect, by the way. So what we have here is a tensor from elements. This is the same example as before, tensor from elements. We insert into %0, and now we extract from %0. And what we do here in the transform dialect script is we bufferize the entire function. Then we run canonicalization and CSE. I'll show you later why we do that. And then we run the buffer deallocation pass that Martin is going to talk about later, which basically inserts deallocations for everything that we allocate. OK, so this is how you run it. And that's what you get. So an allocation for the first op from tensor, which was not in destination passing style. Then here we have an allocation and a copy because something bufferized out of place. And yeah, here's the load. So let's make a small change to that. Or actually, let's first take a look at some of the debugging options that we have here. So one thing that you can try, if you're wondering why do I have a conflict, how do I debug this, why do I have a copy here that you don't expect maybe, you can say test analysis only equals true and print conflicts equals true. How do I save this? Percent?
Control S.
Control S, okay. How did that work? Yeah, there we go. So as you can see now, the IR was not bufferized. So we just ran the analysis, and this shows you, this gives you some information about why a copy was inserted. So what you want to look for is these C0. So this is basically a counter. So we only have one conflict here, so we only have a C0, but if there are multiple conflicts, you will also have C1, C2, etc. So this is the conflict triplet here. We have a definition, we have the conflicting right here, and here is the read. And also we have this in-place operands utter, which tells you for every op operand whether a copy was needed. In that case, you have a false. In this case, a copy was needed for the insert into from elements. In this case here, it was in place. The extract was in place, so no copy was needed for this guy here. And everything that's not a tensor operand, it just has none. So that's a very useful tool to debug this. So we can fix this program, for example, by by moving this upwards. Or how do I cut this here? Control X or
you can control
cut. Oh, that also works. Okay, paste. So now we have the extract first, and then we have the insert. So no, didn't save. Ah, there we go. So now we have the extract first, we have the insert here, and everything here says true, so there are no conflicts. No copy is needed here, no buffer copy. Another useful thing that you can try is if you're curious about what kind of, if you're wondering if you have implemented your get aliasing values function correctly, there's a flag to dump the alias sets. And as you can see now here, the bufferization decided that % inserted and % from elements share the same buffer. That's why they're in the same alias set. So this is also something you can query here. Okay, then I have a second, slightly more complicated example. So what we have here is a batch matrix multiplication. And this is the example that you saw before, but not as a tensor op, but as a linear op. And how to get to this point, that's what I will talk in the next few slides. But we have two inputs, one output, %c. So that's where we, so basically the linear op is in destination passing style. That's why you directly tell it where the result should be stored. This is this %c here. You have to fill it with a 0 before, because the semantics of the op is that you plus equal the result into the destination. So you have to fill it out with zeros. Otherwise, you add the result to whatever was in the op before, in the buffer before. And finally, we want to have the result stored in %c. That's what this bufferize, materialize in destination says. Okay, let's run this. There we go. And what you see, oh yeah, one thing I did also here, I ran a tiling operation. So maybe, so what I did here, okay, let's delete this. Let's take a look at this step by step. So first thing I did here is tile the lin-like operation, because in the next step I want to simulate a bug here. So we tile the matrix multiplication, and now we have a loop nest here, and we extract from the source and from the destination, and then so this is how you tile in MLIR with this tile using for. Now so now after that we run the canonicalizer and bufferize, and it looks did I have, okay. Oh, did I accidentally write something here? Yeah. Yeah, that's what it looks like. And at this point, I want to highlight that earlier I said we always canonicalize after bufferization. And the reason for that is that you can see in this bufferized code, we have a MemRef copy, and we copy from a subview to another subview. So everything bufferized in place here still with a MemRef copy. That's because the way the bufferization works, it bufferizes op by op. And before you bufferize the terminator, the terminator basically has to bufferize to a copy, because otherwise you could have some IR that was not bufferized yet, and it's still tensor IR, it's not used anywhere, and it will just fold away. But as you can see, these two subviews are actually identical. And after we run the canonicalizer, let's go back here. So after we run the canonicalizer and CSE, all of these copies are gone. Okay, there's one more thing I want to show here. In this example here, I simulated a bug in the bufferization. So in the tiling framework, actually. Instead of extracting from this eta arc here, I directly extract from arc4. So we can assume that something went wrong in the tiling algorithm for some reason. So if we run this, we see that something bufferized out of place. So we have a copy in here and an allocation. So now we can do the same thing as before. So let's delete this. Let's take a look at why we have a copy. Oops, should be true. And as you can see here, there are actually two reasons why. There are actually two conflicts, two copies were inserted. But I'm only going to talk about one here, and the one inside of the loop. So we're looking at conflict number 1. Yeah, as you can, so we're looking for everything that starts with C1. So here is the definition. The definition is the basic block argument of the outer loop here. So arc6, I think. Yeah, so we have a definition, no, arc4, sorry, that's the one. So that's where some data is being defined by this loop basic block argument. And now in the nested loop, we have this batch matmul, which is both the conflicting write and also the read. So what this is an example for the loop rule that I showed before. Something is defined outside of the loop, and then inside of the loop, we read from the buffer, but we also write into this buffer. And because of that, we have to insert a copy, because the next iteration of the loop may want to read the old data. In this case, that's actually not necessary, because we do tiling, and the next iteration will operate on a different segment of the same buffer, but the bufferization is not smart enough to figure that out here, because this information is obfuscated by going through a loop basic block argument. Okay, now let's go back to the presentation. One optimization that I would like to talk about is the so-called empty tensor elimination. And tensor empty is an op that we have in a tensor dialect, which basically which specifies a tensor of a given shape, but without saying what's inside. So this simply bufferizes to memref alloc. And this op is often used by transformations that convert ops into destination passing style. An example would be TOSA to linarg. So if you have a TOSA matmul, as in the original example, if you run this pass, it will lower it into a tensor empty, linarg fill, and then a batch matmul. And this batch matmul is in destination passing style. It has an output here. It's not very useful in this case because the output is essentially a tensor empty, which bufferizes to a new allocation. Yet, at least the ops that we have here are in destination passing style. And if you put the other ops around that we saw in the original running example, we say that this %r should materialize in the buffer %c, materialize in destination. And this will, as you saw in the demo before also, this materialize in destination bufferizes to memref copy. So what we have here is we allocate a buffer, we fill it, we store the result of the matrix multiplication in there, and then we copy the entire buffer over to %c. At which point you may ask, why don't we just store the result in %c directly? And that's what empty tensor elimination does. So it literally eliminates the tensor.empty. So it looks for this materialize in destination, traces it back, sees, oh, I'm going to, the thing that I'm inserting is originating from a tensor empty, and then it replaces it with the corresponding destination. In this case, bufferization to tensor. And the bufferization materialize in destination here will still bufferize to a mem copy, but it will copy from %c to %c, and then it will fold away. And this is how we can handle ops that are not in destination passing style. We convert them into destination passing style, run empty tensor elimination, and then we bufferize them. So I have a few demos for that, but let's first talk about buffer deallocation. And if we have time, we're going to look at those afterwards.
Thank you, Matthias. So I'm going to talk about buffer deallocation, which is to be run at the very end of the overall bufferization pipeline, specifically after the optimization passes that already run on memref IR. For example, buffer hoisting and promote to stack, which do not support pre-existing deallocation operations in the IR. So on the right-hand side, you can see the example that Matthias already showed you just after bufferization. And you can see that there is one memref that you get as a function argument and one new allocation in the then branch of the SCF if. And you can see that there is no memref returned from the function and no deallocation present yet. So if the then branch of the SCF if is executed, there would be a memory leak. So the old deallocation pass would just insert a new allocation in the else branch of the SCF if and copy over the contents of the memref you got as a function argument. That way the pass knows for sure that the memref returned by the SCF if is a new allocation, and it can just insert an unconditional deallocation at the end of the function body. The problem here is that this is very inefficient, especially if the memref is really big and if the else branch is the more likely branch taken. The old deallocation pass also had other issues. Most importantly, it leaked a lot of memory, especially around function calls, but also in unstructured control flow regions. And it had the assumption that buffer writes always have to dominate buffer reads, which is not guaranteed by one-shot bufferization. So what the new ownership-based buffer deallocation pass does is inserting a conditional deallocation at the end of the function body. And you can also see that there is this extract threaded metadata operation inserted. That's just to make sure that the deallocation, memref dealloc op gets the originally allocated memref, because that's a requirement of that op. The ownership-based buffer deallocation pass has a default implementation, which considers the common interfaces in MLIR. So if you have an op that has a region and implements the region branch up interface. That's just supported by default. Also for terminators that implement the branch up interface or the region branch terminator up interface. But we also have an op interface called buffer deallocation op interface that you can implement for your custom operations if you cannot implement those default interfaces like region branch up interface. Or you can also use it to refine what the deallocation pass does to generate a more efficient IR. To give a brief overview and a little comparison of the old versus the new pass. So as already mentioned, the old pass had this assumption that the buffer writes must dominate the buffer reads. That's not the case anymore for the new deallocation pass, so it can be used safely after one-shot bufferization. The old pass did not support unstructured control flow loops, whereas the new one does. The new one also defines a proper function boundary ABI, which has the disadvantage that the input IR needs to adhere to it. But on the positive side, it's the function boundaries are handled consistently, and you can implement canonicalization optimizations against that. Then what the old deallocation pass supported to some extent is existing deallocation operations. That's not supported at all in the new buffer deallocation pass, but there is an option that you can enable to just delete all the existing deallocations and let the deallocation pass insert them again. And as already mentioned, we have an op interface to refine the lowering. So the new buffer deallocation actually is a pipeline that consists of 5 passes. First, we have a pass to expand the MemRef realloc operations, because this op has a deallocation side effect, which we don't support. So we expand it to this conditional allocation, but do not insert the deallocation operation. Then we run the actual ownership-based buffer deallocation pass, which inserts the bufferization.dealloc op, which we're going to talk about in the next few slides. And then we have a pass to optimize this bufferization dialog op, and afterwards we lower it to memref.dialog or your custom dialog operation. So the new deallocation pass is based on the concept of ownership, and ownership is a property of the allocation itself. So aliases of an allocation just have the same ownership and are not considered individually. The owner of an allocation or of a memref is always a basic block, and the bufferization dialog op models a conditional deallocation. So you give it a list of memrefs that you potentially may want to deallocate, and the op determines whether they should actually be deallocated. So the condition under which it is actually deallocated depends on the ownership, so whether the basic block in which the deallocation operation is in actually has ownership, whether an alias may still be used afterwards, for which also liveness analysis is used. And implementing this op allows us to have a simpler deallocation pass, provide the optimizations in a subsequent pass, and have specialized lowerings for more efficient codegen. So this is how the deallocation op looks like. It has a list of memrefs that potentially need to be deallocated and their ownership indicators, which are just I1 values. And obviously they need to be the same, need to be the same number. And it has a list of retained memrefs, which are essentially the memrefs that the aliases that may be used afterwards. So let's go over a simple example to see when M1 should actually be deallocated. So first we're going to check if own1 is set to true, so if the basic block actually has ownership. If that's not the case, we just don't deallocate. If it's the case, we also check that if one of the retained MemRefs originate from the same allocation as M1, and if that's the case, we don't deallocate to avoid use after free cases. And for M2, we additionally check if M1 originates in the same allocation and was already deallocated to avoid double deallocations. And then we also check the ownership and the retained operands. By construction of the deallocation path, we know for sure that all the MemRefs that the basic block potentially has ownership of are present in this first list, which is important for to compute the result values of the deallocation operations, which represent the new ownership of the retained operands. So to compute the first result, we start with false as the default value. Then we check if R1 originates in the same, from the same allocation as M1. And for the purpose of this example, let's assume that's the case. So we add the result of this is same buffer analysis conjuncted with the condition with the ownership of that M1 to our result value. And by our assumption, we know that the result of the analysis is true, so we can fold it away and end up with own1. And then we do the same for M2, and here we assume that they do not originate in the same allocation, so the result of the is-same buffer analysis would be false here, and then this chunk folds away. The bufferization dialog op also has this lowering pass afterwards. We have one default lowering, which has a runtime of the number of MemRefs to potentially deallocate squared plus the number of dialogs times the number of retained MemRefs, and a space requirement of total number of operands. This lowering requires a library function to be inserted to avoid code size explosion, and thus has to be a module op pass. But we also have some special, some optimized lowerings. One for the case where we have only one MemRef to dialog and no retained operands, and one where we have only one MemRef to dialog and an arbitrary number of retained ones. Here we don't need to insert the library function, and thus it can be a function pass. But if you make it a function pass and you actually need the library function, it would throw an error. So we would also have some demo here, but I think...
Do we still have time? The timer says 1 minute here. Yeah. Oh, okay, yeah, so we still have time.
You can do your demo first, I guess.
Yeah, no, just do the buffer deallocation demo.
Okay, so we have this IR that I already showed before. We have some allocations in here and an outer and inner for loop, and there are no deallocations present yet. So at first we can go ahead and run the buffer deallocation pass, which just inserts the bufferization dialog ops. Copy that. Now going from the innermost loop, we see this bufferization dialog operation in here. It has this allocation that was allocated in this inner loop and true as a condition, so this would just lower to an unconditional deallocation. And then in the outer loop, we also have this allocation here, which is present in this deallocation op, plus the MemRef that we got as an iter arg from the loop. And that one has as a condition the ownership that was passed in as an additional iter arc here, which was inserted by the buffer deallocation pass. So ownership is never given to nested regions, so that's why we have false here. But in the yield, we return the result of the buffer dialog, which might be true. And at the end, we have a bufferization dialog that contains all the three MemRef function arguments, which have all false as ownership, which is according to the function boundary ABI, and the result of the for loop. Now we run the optimization pass, and then we can. That's not the one. So here we can see that this dialog hop was optimized, so there is no extract-threaded metadata for this allocation anymore. And for the last dialog, we can see that all function argument MemRefs were optimized away because the ownership condition was always false. And after that, the lowering of the dialog hop is called, which lowers the bufferization dialog hop. And we can see that this dialog helper library function is inserted, which is used for the last dialog hop. And we can see that there is a lot of IR inserted to set up the function call to the helper library. So you really want to avoid this general lowering if possible. But the other deallocation operations were lowered to an SCF if with MemRef dialog inside.
Good. Going back to the slides. Yeah, so these are the passes again that we were talking about. So preprocessing is basically the rewrite in destination passing style, Tosa to Linarc, but we also have lowerings for ops such as tensor from elements. So that's why there's a transform op which is called rewrite in destination passing style. Empty tensor elimination, which removes the tensor empty, so we write into the destination directly. Then one-shot bufferize, the actual rewrite and bufferization to MemRef, and the new buffer deallocation pipeline. So at the moment in MLIR, we still have this old buffer deallocation pass. It's still there, but as Martin said, it has issues, it has memory leaks, it's inefficient because it inserts copies when you have branches where one branch allocates, the other one doesn't. So we would recommend that you give the other buffer the new ownership buffer deallocation pass a try, which you will find by running this pipeline here. And the plan is to eventually remove the old buffer deallocation pass, but it's still quite heavily used in various other projects, so we will keep it for the moment. Yeah. All right.
We have 5 minutes for questions, so if anyone has questions, step on up.
Yeah, if something comes up, if you run into issues with copies, feel free to also message us on Discord. It happens quite often, and bufferization is a tricky topic. People often get confused. Why do I have allocations here? And happy to look at it together. Also, if you can send me the IR, I can explain why there's a copy here, and maybe we can also discuss how to improve debuggability and so on.
All right, thank you very much. The next talk will start at 15 after the hour, 2:15. So